everyone, I'm Frank Xu, and I'm MacDermid Alpha's Technology Manager for Surface Finishing. And I joined the company over 15 years ago. I have a PhD degree in Material Science and Engineering. I'm also a Six Sigma Black Belt. Welcome to our 5-minute overview on high-frequency surface finishing. Despite incremental process improvement, the surface finishing options for both PCB and IC substrate have not significantly changed over the last 10 to 15 years. However, with the introduction of the 5G mobile networking, creating growing demand for smartphones, networking, and wireless connections, all require increased data flow. The need to reduce the signal loss at higher frequency bandwidth is becoming vitally important. As a result, fabricators are once again looking to newer generation surface finishes to meet their performance criteria. Today, I'd like to take a little time to introduce some of MacDermid Alpha's test data as we work to understand how these new-to-market surface finishes perform against typical surface finishing requirements. As we map out the attributes of the traditional surface finish options, OSP, emulsion tin, emulsion saver, ENIC, and ENIPIC, you can see from our traffic light system that low one finish shows a strong performance against all requirements. Traditional surface finishes are generally selected on a performance versus cost basis, and you can see from the diagram that as we move from right to left, OSP towards the ENIPIC, we gain improved functionality from the finish, but also at higher cost. However, performance at high frequency doesn't follow the trend of better performance with increased cost. The low-cost finishes, such as the emulsion saver and the OSP, have good performance at higher frequency, but lack some of the other performance requirements, such as wire bonding. You may have heard people interchange high-frequency finishing with nickel-free finishing. Electroless nickel layers have served well as a barrier layer for copper diffusion, giving ENIC and ENIPIC finishes robust shelf life. But there are issues associated with electroless nickel. The first issue is related to miniaturization. Electroless nickel is relatively thick compared to other finishes. Typical EN thickness of 3 to 5 microns could increase the trace or pad dimension by 6 to 10 microns, which will limit capabilities to build tight-spaced structures, as well as posing extraneous plating problems. The second issue lies in the fact that EN is a ferromagnetic and also a poor conductor. As frequency of operation increases, electrical signal travel more to the edge of the conductor, meaning the surface finish carries the signal more, and the properties of the finish have great effect on the signal integrity. As can be seen on the slide, previously published signal loss data shows that emulsion saver and OSP perform similarly to bare copper, but ENIC and ENIPIC show increased signal losses with the frequency increase. To assess the effect of surface finish, MacDermid worked in partnership with Rogers. The dielectric substrate, copper foil dielectric interface, circuit definition, as well as the surface finish have effects on the results, and this needs to be taken into account when testing. The microstrip test vehicle, amongst other features, utilizes 2 different length strips repeated on a thin, low-loss Teflon substrate with smooth copper. The test vehicle is cut in half, with one half processed through the surface finish test candidate and the other half remaining copper only. Using a vector network analyzer, the phase shift between 2 strips at different frequencies can be measured and the signal loss may be calculated. As we know in previous slides, nickel is a culprit to excessive signal loss. When designing new surface finishes, we either reduce the nickel thickness down to 0.1 to 0.2 microns, we call it a thin nickel ENIPIC, or eliminate the nickel totally, such as EPIC, the palladium gold finishes, or silver gold finish. The standard ENIPIC, ENIC, emulsion saver, and OSP are used as references. To create a simple way to analyze the effect of surface finish on signal losses, we constructed a stacked bar chart broken down into 2 components of signal loss. The total height of the stacked bar represents the total signal loss from construction and the surface finish. The blue bar describes the signal loss from the construction, and the red bar shows additional signal loss from the surface finish. We selected the 3 typical frequencies to evaluate the data. The 6 GHz, which is typical for most applications, 40 GHz is typical for 5G application, and the 77 GHz that's typical for ADAS system. As expected, unique and unipeak deposits with typical EN thickness of 4 microns can add significant signal loss. In some cases, the signal loss is almost as much as the construction of the design, and thus there are concerns about limited performance. Emulsion saver and OSP do not contribute to signal loss, and by far the best surface finishes for the high-frequency performance. The new generation surface finishes test candidates all showed similar signal loss performance. Silver gold, thin nickel unipeak, as well as EPIC were all within experimental error of one another. Previously published data has shown that signal losses can be reduced by reducing EN thickness, but we found it interesting that very thin EN layers give similar performance to no EN finishes, such as silver gold or EPIC. It was surprising to find that silver gold and EPIC with no EN layer produced some signal losses. Insertion loss testing shows that full thickness EN finishes have limited performance, and that emulsion silver and OSP finishes did not add any signal loss to the construction. However, emulsion silver and OSP lack other areas of functionality that may be needed, such as wire bonding, and thus other selection criteria become important for differentiation when selecting between alternative surface finishes. In part 2, I will compare the performance of the surface finish test candidates for ball shear, drop shock, wire bonding, mixed fluorine gas, as well as the solder joint reliability under thermal and high current density stresses. Thanks for taking the time to watch our video. I hope it's been of interest. Please look out for part 2 of this study, coming soon to the MacDermid Alpha's LinkedIn page. In the meantime, if there are any questions, please feel free to reach out. My name is Fang Xu, and my contact details are shown here.